Hi, everyone. This summer, news headlines have consistently highlighted the prevalence and impact of forest fires. Today, I'm going to introduce two forest fire prediction frameworks that harness the power of the machine learning technique federated learning combined with the real time data collection and remote monitoring capabilities of Internet of Things technologies. My work is part of an NSERC Alliance mission grant collaboration with the University of Waterloo, Carleton University, Dalhousie University, and Sistel Technology. First, I'd like to present the key motivators for my thesis. Second, what's the current state of forest fire prediction both in terms of machine learning and IoT? Next, I'll present this thesis's framework for creating forest fire prediction datasets. The core of this thesis is a federated learning framework. I'll outline and demonstrate its key elements with a simulation. In conclusion, I'll look at the limitations and future work. Forest fires pose a significant threat, endangering lives, devastating communities, impacting air quality across vast areas, and contributing to climate change through carbon emissions. On August 9th of this summer, fanned by winds from Hurricane Dora 800 kilometers to the south, forest fires destroyed the town of Lahaina, Hawaii, killing over 100 people. In Kelowna, British Columbia, on August 18th, rapidly moving fires destroyed the historic Lake Okanagan resort, many nearby homes, and led to the evacuation of thousands. At the same time, 20,000 people were being evacuated from Yellowknife in the Northwest Territories as fire approached the city from three sides. Anticipating the conditions that can lead to forest fire ignition is pivotal for safeguarding vulnerable communities and optimizing firefighting resources. Over the last 4 decades, both in Canada and globally, instances of forest fires have surged in numbers, frequency, and intensity. Consequences of weather events such as heat domes brought on by climate change point to this trend continuing. Despite significant research efforts, most existing forest fire ignition prediction models are empirical, while the potential of machine learning techniques remains largely untapped within current fire management systems. Datasets are essential for robust testing and training of machine learning models. There's a lack of comprehensive datasets that integrate forest fire ignition data with pertinent variables like weather data. Finally, the Weather Guide for the Canadian Forest Fire Danger Rating System notes that a much larger network of fire weather stations is needed if reliable fire weather forecasts are to be prepared at a scale suitable for efficient and effective fire management. To this problem and the potential of machine learning techniques for forest fire prediction, this thesis proposes using Internet of Things technologies and federated learning. To answer the question, how can the integration of federated learning and IoT technologies enhance efficient forest fire ignition classification prediction? This thesis proposes two frameworks, a framework using federated learning for IoT-based forest fire prediction, and a framework for creating forest fire ignition prediction datasets. There are thousands of fires every year in Canada, burning millions of hectares of forests. Natural Resources Canada provides fire information to fire management agencies and the public through the Canadian Wildland Fire Information System platform. Any framework that's going to address the forest fire ignition classification prediction problem needs to augment this system. There are three key pieces of information that the Canadian Wildland Fire Information System provides. The fire behavior forecast gives an indication of where a fire is most likely to go once it starts. M3 hotspots are satellite identified points where fires currently are. And the most relevant to this thesis, the fire weather forecast is the probable intensity of a forest fire if an ignition occurs. It has been shown that this is also an indication of the probability of a forest fire given an ignition. At the root of this prediction is the fire weather index. This is an empirical model that takes 4 inputs, rain, temperature, relative humidity, and wind, and results in 6 outputs. The top 3 outputs are moisture measures correlated to combinations of rain, temperature, humidity, and wind. The middle 2 provide information as to how a fire will behave once it is started. And the bottom fire weather index provides the probable intensity and, by association, the probability of a forest fire. And in graphic form, it becomes the fire weather index map we saw earlier. The Canadian Wildland Fire Information System uses several sources of data. Ground-based solar-powered automatic weather stations are key to gathering information specific to the forest floor. Permanent weather stations are augmented by temporary ones that can be deployed to an area at risk of ignition or an area that has already experienced a forest fire and needs to be monitored for reoccurrence. Considering the common definition of IoT as a network of physical devices with sensors, software, and connectivity, the Canadian Wildland Fire Information System has been utilizing IoT since its inception. In general, forests are increasingly becoming smart, equipped with IoT devices. These devices serve various purposes, such as monitoring forest health and disease, tracking logging activities, and measuring changes in forest structure. Searching IEEE Explore using the keywords forest fire prediction showed an increasing number of research papers using machine learning in the time period from 2014 to 2022. Papers could be divided into two types, those that tested machine learning models and those that implemented IoT systems. Usually, the machine learning papers did not discuss implementation, and the IoT papers seldom used large enough data sets for good results. The papers were looked at for what data set, machine learning algorithm, and what metrics were used. In total, 38 papers were found to have relevant aspects to this thesis. Most often used and most successful were decision tree type models such as random forest and XGBoost. Neural networks, however, became more prevalent in papers closer to 2022. Time series models, RNNs, like LSTM, showed a lot of promise but only showed up in a few well-researched papers. There was no published research at the time I was searching with respect to forest fire prediction using federated learning. The original paper where McMahon and al. Coined the term federated learning is still an excellent resource for this thesis, though. It presents the distributed computing concept where clients maintain their own datasets and machine learning models. The model is federated by sharing weights with a central server that averages the weights and shares them back to the clients, with the principal benefit of communication cost reduction and data privacy. With all this background in mind, I proposed a federated learning system using IoT collected weather data from ground-based sensors that could augment the forest fire ignition classification prediction capabilities of platforms like the Canadian Wildland Fire Information System, where IoT weather stations, each with their own model and local data, could share weights with a central aggregator. However, datasets that could be used to simulate such a system did not exist. Before I could look at federated learning for forest fire prediction, I needed a machine learning model to federate, and before I could train and test a machine learning model, I needed a dataset. Datasets that existed were few, not generalizable to Canadian regions, and contained too few data points to divide into smaller datasets. Data creation was approached from a framework point of view with multiple inputs, some processing, and then a single output in tabular CSV format. My tentpole data was ignition data, whether a geographic area had an ignition or not at a specific time. My primary feature data was chosen to be weather data. This is based on the Canadian Wildland Fire Information System and the correlation between climate change and the increased forest fires that we're seeing. Past research looked at other feature sources such as proximity to lightning strikes, terrain features, and human infrastructure. I chose to leave this for future work and put that in the framework as other sources. A boundary source was necessary to limit the amount of data looked at. These were combined and an output was generated. To test the framework, I instantiated it for a fire-prone region of British Columbia. BC has an excellent ignitions records going back over a century. Weather station collected data for BC is readily available, but collection points are not evenly distributed and the data is temporally inconsistent. Reanalysis data, however, is a commonly used and validated solution when weather data is not available. Data is generated using a machine learning algorithm trained on weather features from various sources. The reanalysis weather data I used was from the European Center for Medium Weather Forecasting. Both feature and ignition data were masked and combined, producing a data table. In this sample of the first two rows of the dataset, we can see longitude and latitude location of the features, such features as wind speed, air temperature at 2 meters above the ground, soil temperature at various levels, soil moisture at various levels, the day of the year, and the year. Note, this sample doesn't have time of day, and whether or not an ignition occurred on that day in that location. To test the fitness of the dataset, and by fitness I mean the degree of suitability of the produced dataset for the specific task of forest fire ignition prediction, we trained machine learning models that have been previously utilized in forest fire prediction research. Sensitivity, or recall, is a good measure of how many of the true positive predictions, that is to say ignitions, that the model got right. In the case of our instantiated dataset, random forest performs well, which is consistent with past research, and all of the other models, however, were clustered fairly close, with the exception of logistic regression and SVM. Nearest neighbor performs best in terms of specificity, the measure of false positives, but the other models from past research are pretty close to it, again with the exception of logistic regression and SVM. Other metrics like accuracy, receiver operating curve, and the area under the receiver operating curve and precision also perform similarly, indicating the datasets produced by the framework were fit for forest fire ignition classification prediction. So what metrics does this thesis use and why? Accuracy isn't a good measure when using imbalanced data, which forest fire ignition data is. Typically, there's an extremely low number of ignitions to a high number of non-ignitions. I include accuracy, however, since it is a predominant metric in past research. Recall, also known as sensitivity, measures how many ignitions the model got right. Specificity measures the rate of falsely reporting ignitions. In real terms, this could result in allocation of resources where they're just not needed. The receiver operating curve plots sensitivity or recall against specificity. This is relevant in forest fire prediction since you want to balance how many ignitions you correctly predict against the number that you falsely predict. Essentially, how much error can you tolerate? And finally, instead of having to choose a specific recall or specificity value on the receiver operating curve, the area under the receiver operating curve gives a single value measure of how well the model is doing in the realm of true positives versus false positives. With that in hand, now I'd like to introduce the framework for predicting forest fire ignitions. It's comprised of three components: a network of IoT weather stations collecting data, each weather station with a similar machine learning model, and a central aggregator. Local model weights are shared with a central aggregator at regular intervals. The central aggregator averages the weights, and the new average weights are returned to all weather stations in the network. Each local weather station outputs a forest fire ignition classification prediction of non-ignition or ignition at regular intervals. Looking at the framework schematically, we see local IoT weather stations, each with its own local data and local but similar model, and the central aggregator the IoT weather stations communicate with. Looking at the processes within an IoT weather station, weather data is collected and stored. The local model is trained, local weights are sent to the local aggregator. The central aggregator averages the received weights and sends them back to all of the local IoT weather stations. The new weights are received and the local weights are updated, ready for training on the next set of new data. To evaluate the performance and effectiveness of the Federated Learning Framework, it was implemented as a simulation. The Forest Fire Ignition Dataset Framework was instantiated for a fire-prone region surrounding Kelowna, British Columbia. Reanalysis weather data was downloaded from the European Center for Medium Weather Forecasting at the finest available resolution. I arbitrarily chose to divide the region into 24 cells, and the weather data within a cell was averaged to represent an IoT weather station with its own local weather data. A central aggregator was imagined to be at the center. A simple LSTM model was developed, and the data was converted to time series data, with each row of the data representing 120 hours or 5 days. So within the simulation, A goal was to gauge the effectiveness of the instantiated federated learning system where IoT weather stations collected data, trained a local model, and transmitted local weights to a central aggregator. And the central aggregator averaged the weights from participating IoT weather stations, transmitting the averaged weights back to the local stations that output forest fire ignition classification prediction for the local area they represent at regular intervals. To act as a control to compare the federated system against, a simulated IoT weather station network reporting to a single central server was also imagined, where IoT weather stations distributed in the same manner as the federated system collected data and transmitted it to a central server at regular intervals. The central server stored the data and trained a LSTM model similar to that used in the federated system, outputting a forest fire ignition classification prediction for the entire region. Could the federated system achieve comparable results to the centralized system? Using the Flower Federated Learning Library, I set up 4 experiments, comparing a centralized server system, CS, to a federated learning system, FL. In terms of training epochs, the centralized system always used 100 epochs. In experiment 1, simulated IoT weather stations trained their models for 3 epochs per round, a round being a full train send average cycle. Experiment 2 for 6 epochs, experiment 3 for 12 epochs, and experiment 4 for 6 epochs. As mentioned, a round is a full train send average cycle, or more officially, the reporting of weather data for a specified time and the subsequent retraining of an existing model using that weather data plus historical data. This doesn't apply for the centralized server system in this simulation. For the federated system, all IoT weather stations updated the model weights over 3 rounds, with the exception of experiment 4, where 6 rounds of training were run. Both systems used the same LSTM model and time series data where each row represented the arbitrarily chosen value of 120 hours. 24 simulated IoT weather stations were used for all experiments. This number was determined by the availability of data and hardware limitations. In a federated learning system, not all IoT weather stations need to be useful for training. This allows the dropping out of outliers, providing inconsistent weights, and also reduces transmission energy and processing requirements during the averaging step. In the case of this simulation, 18 stations were randomly used from the 24 available each round. 18 reflected hardware limitations. Again, in a federated learning system, not all IoT weather stations need to be used for evaluation. Ideally, all 24 stations would have been evaluated per round, but due to hardware limitations, 18 were randomly chosen per round instead. So what do the results look like? Here's a sample from experiment 2, where each IoT weather station trained its model for 6 epochs per round, and there were 3 rounds. I've arbitrarily chosen 3 stations here, station 1, 8, and 16. Looking at the results from station 1, the metrics show decent results in round 1, and over the next 2 rounds, there's some improvement as the results from all stations are averaged, but nothing significant. Station 8 and 16 show similar results, as do all the stations. And to get a sense of overall performance, the results from all the stations were averaged and compared to the centralized server system. Results were similar between the centralized server system and the federated system. Recall is significantly worse in experiment 4, the one with 6 epochs and 6 rounds, though. Overall, the federated system achieves comparable results, though slightly worse, to the centralized system in terms of metrics. Looking at the spatial granularity, however, the federated system is identifying ignitions at 24 times the resolution of the centralized system. Considering the communication energy of the 2 systems, are they equal? The communication energy for the federated system is made up of the number of IoT weather stations, size of model weights, reporting frequency per round, sum of distances squared between weather stations and central aggregator, and a constant of proportionality that resolves some unit issues. The communication energy for the centralized server system is made up of similar variables. The key difference is the federated system transfers weights back and forth to the central aggregator once per round. The centralized system transfers data at regular intervals, and the number of transfers is determined by the space between intervals. Let's consider an example. Using data sizes from the simulation where a weight transfer between an IoT weather station and the central aggregator is 20 kilobytes, and each data transfer between an IoT weather station and the central server is 0.094 kilobytes. The time between retraining the model is 1 week. So the federated system has 24 weather stations, 20 kilobytes is transferred to the central aggregator, and 20 kilobytes is transferred back to each weather station for a total of 2 transfers, resulting in 960 kilobytes being transferred over the distances between the weather stations and the central aggregator. The centralized server system has 24 weather stations. 0.094 kilobytes is transferred to the central server every hour for 168 hours, resulting in 379 kilobytes being transferred. Now let's change the time between retraining to 336 hours. The centralized server system has 24 weather stations. 0.094 kilobytes of data is transferred over 336 hours, resulting in 758 kilobytes being transferred. Still less than the federated system, but we can see at some point the federated system is going to be less than the centralized system. Now, let's not use all of the weather stations for training during the federated learning system. The results in the federated system use less communication energy. In a graph, we see that the communication energy used by the federated system is flat, but the centralized server system has a linear relationship between the amount of data transferred, and thus communication energy, and the time between model retraining rounds. Summarizing the results and the thesis, a framework for producing forest fire datasets was introduced. 3 datasets were produced suitable for simulating IoT weather station data. The fitness of the datasets was evaluated using various machine learning models. A framework that combines federated learning with IoT weather stations was introduced. Using a simulation, it was demonstrated that performance between the federated learning system and the centralized server system are comparable. The federated learning system exhibits better prediction spatial granularity than the centralized server system. And in some cases, the federated learning system exhibits better communication energy performance than the centralized server system. There are several avenues for future work. The datasets created were only cursorily compared to existing weather data. A comprehensive validation of the feature values would strengthen the value of the datasets. IoT weather station deployment may be limited by terrain and expense. Data collection could be expanded beyond IoT weather stations to UAVs and mobile phones carried by campers, forestry personnel, and forest firefighters. Fire weather is a nuanced topic. Involving climatologists, indigenous peoples, and experienced forest firefighters in early stages of feature engineering may result in significant gains in modeling metrics. New machine learning paradigms like transformers may be better suited to the unbalanced time series problem presented by forest fire prediction. To date, the frameworks have only been applied to regions of a certain topography and climate. Datasets for all the provinces of Canada need to be produced and tested together, and then experimentation needs to extend beyond the climate and terrain we find in North America. There are multiple unexplored federated learning avenues, such as the optimal number of training stations used and time between retraining. So in conclusion, this thesis demonstrates the potential of integrating federated learning and IoT weather stations to enhance forest fire ignition, classification, prediction capabilities of fire management platforms like the Canadian Wildfire Information System. Based on this thesis, a paper has been submitted to the IEEE Transactions on Geoscience and Remote Sensing, and a paper has been submitted to the IEEE 2023 International Conference on Internet of Things and Intelligent Systems. Thank you to my defense committee, my supervisor, Dr. Sampali, and the supervisors and students that make up the NSERC-sponsored collaborative project that this thesis grew out of. Thank you for listening.